Section 4.5, number 83, is a 7-part question. We'll just go over the first 5 parts. Mind you, in your homework, your values might be different, so your question might be slightly different than this one. We're told that suppose x is normally distributed variable with mu, the mean, equal 30 and standard deviation equal to 8. Find a value of x naught, that's x subscript 0, that would make the following true. Alright, so for part A, we're told that the probability that x is greater than or equal to x naught is 0.5. What this means is that we're given a normal distribution, and we know that for the normal distribution that it's centered around the mean, and we're told that the true mean is equal to 30, so we can draw this center around 30. The area underneath the curve represents a probability, and since the probability that x is something is 100%, just any number from negative infinity to positive infinity would be 100%, that means the area would be 1, because 1 is 100%. That also means that the area on 1/2 of the curve would be 1/2, or 0.5. Alright, so basically areas under the curves represent probabilities. We want to find the probability that x is greater than or equal to 30, we want to find the x value such that the area to the right is 50%, and this area is 50%. So that means our x naught value must be the mean. It must be 30, because half of the curve, since the normal distribution is symmetric about the mean, half is above and half is below. Alright, so we didn't need to do anything too complicated there. It's just more understanding that for every normal distribution it's centered around the mean, where half is to the right of it and half is to the left. Okay, the rest of these are a little bit trickier. Again, I'm going to start off by drawing my normal curve, centered around 30. And we're being asked to find an x naught value such that the area to the left of it, and left because of this not because it's less than sign, the area to the left is 0.025. Well, 0.025 is very small, and we want to do the area to the left of it. So that means our x naught value has to be somewhere over here on the left-hand side, because this area here is only 2.5%, or 0.025. At this point, there's several ways you could approach this question. If you have a TI-83 or 84 calculator, you can use a function called inverse norm. I think it's called inv-norm, something like that, inv-normal. To solve this, you could use StatCrunch to solve this. I believe Excel can even solve this, but let's just, assuming that they have limited technology, we can do this with a statistical table as well. We're told the area to the left is 0.025, but our table always gives areas, if we look at z-scores, always gives areas between 0 and some z value, like this. Because of symmetry, we could even use this table for negative z values as well, when z is less than 0. And these would be the same thing. These are the same values. So in other words, we're given the area of the tail here, but what we really want is the area between 30 and our x naught value. Those will correspond with z-scores between 0 and some z value that we don't know. So because we know half of the curve is to the right of the mean and half is to the left, we know that this region here, this big region, is 0.5. But we don't want to include this shaded part here. When we look it up on the table, we just want to include the striped part here. So what we can do is we can take our 0.5 and subtract off the tail that we don't want to look up on the table. And so that gives me 0.475. So 0.475 would be the value we'd be looking up on the normal distribution table, but we'd be looking it up backwards. We'd be looking it up in the probability section. So unlike the previous questions where you're given a z and then from that you find a probability, we're given a probability and we're going to use that to find a z-score. Alright, so if we have 0.475, looking at the probabilities on the table, and they are in increasing order, so it's not too bad to find. 0.4750 actually exactly is on the table, and that's associated with a z-score of 1.96. So we know our z is 1.96, but because it's to the left of 0, it's actually going to be a negative 1.96. Now how do we figure out what our x value is, that x naught value? Well, we have a formula. Well, we're told, let's backtrack for a second. We know z is equal to x minus mu over sigma. If you do a little bit of algebra and solve this for x, you can get that x is equal to, x is equal to mu plus z times sigma. And I'll give you this formula on the formula sheet, so you don't need to memorize it, or you don't need to use the algebra to solve for it. But this formula goes right into this one. It's just the inverse. It's just the original formula solved for x. So let's use that formula and figure out what our x naught value is. So that x naught value is going to be whatever the mean is, which is 30. So then we're going to add a negative, so that's a subtracting 1.96 times sigma. Sigma being 8. Then we can take out a calculator. Let's see, we have 30 minus 1.96 times 8, and I get 14.32. Okay, let's do another kind of like this, part C. Actually, part C is very similar. Let's do part D. So for part D, we're asked to find we're said that the probability x is greater than some x naught value is 0.95. So drawing that picture out, and even if you're using a calculator technology, I still recommend drawing the picture, because it'll help you figure out what's going on. We know that the distribution is centered around 30. That's the mean. Z is centered around 0. We want the area to the right of our x naught value to be 0.95. Well, that's a very big area, so that's going to have to be somewhere over here to include well over half the curve. So we know this whole region here is 0.95. Alright. We know that this part here is 0.5. It's half the curve. Half is to the right of 30, of the mean. So that means this region here is going to have to be that 0.95, the whole big region that we were told about, minus the half the curve that isn't included on the z-table. Because remember, the z-table only looks at between 0 and z. Alright, so 0.95 minus 0.5 will give you 0.45. So that's the probability that we're looking up on the table, and again, we're using this table backwards, where we're looking up probabilities and getting z-scores from it. So if we look up 0.45 in the probability part of the table, it's actually, we don't have 0.45 exactly. We have 0.4495 and 0.4505. You could split the difference if you like, and like say, okay, one's at 1.64, one's at 1.65, so that means our z would be somewhere in between that, so that would be like 1.645 if you average those two numbers. Or you could just pick one and go with it, and the computer's flexible enough to allow for that kind of rounding mistake. Alright, so I'll just pick, let's say, 1.65. Normally you just pick the closest value, but again, it's exactly halfway between those two numbers, the 0.45. So anyway, but because it's to the left of 0, it's going to be a negative z-score, so negative 1.65. Now, just like before, we use this formula to figure out what our actual value of x naught is. So it's going to be 30 minus 1.65 times 8, or approximately that at least. So x naught is approximately 30 minus 1.65 times 8. which gives me 16.8. All right, for part E is very similar to the previous parts. It's just written out in a little bit of a longer form. It says 10% of the x values are less than x naught. So really this is almost the same question as B, just with a different number in it. So again, drawing my curve again, doesn't have to be perfect. We know that 10% of the values are below our x naught value, so it has to be somewhere on the left. This area is 10%, so that's 0.10, which means this area here has to be 0.5 minus that 10%, so that's 0.4 or 40%. If I look 0.40 up on the table, again in the probability part, the closest number I find is 0.3997. That's really, really close, so I'll take that. And that's associated with a z-score of 1.28. But again, since we're on the negative side, I'll make it negative. Then using our formula, that x naught value is going to be approximately 30 minus, because it's a negative, 1.28 times our standard deviation. So x naught is, taking out my calculator, 30 minus 1.28 times 8, 19.76. For 4.5, number 85, we're given a story. I just wrote little shorthand notes on it to save a little bit of time, but I'll read the story. It says, again, your homework question might be different numbers. To gauge their fear of going to a dentist, a random sample of adults completed the Modified Dental Anxiety Scale questionnaire. Scores on the scale range from 0, meaning no anxiety, to 25, meaning extreme anxiety. So the higher the score, the more anxious somebody is. The mean score was 11, and the standard deviation was 4. Assume the distribution is approximately normal. And by the way, my shorthand here, it's read as x is distributed normally. That's the squiggle line, the tilde thing means distributed. So x is distributed normally with a mean of 11 and a standard deviation of 4. Just a nice little shorthand to capture that whole story. Three-part question. It says, suppose that you score a 10 on the Modified Dental Anxiety Scale. Find your z-score. So how unusual are you? All right, so we just want to find the z-score. The formula for z-score, let me write it over here, is just x minus mu over sigma, so your value minus the average value over the standard deviation. It's very common for students to accidentally mix up which one's x and which one's the mean. Make sure you keep that straight, that the mean is the second one, or else you're going to get the wrong sign. A negative should mean that you're below average, and a positive z-score means that you're above the average. So make sure you keep that straight, or else you have completely different meaning of your answer. All right, so we want to find the z-score. Our x value was given to be 10. The mean was given to be 11. The standard deviation is 4. So simplify the top first. 10 minus 11 is negative 1. Negative 1 divided by 4 is negative 0.25. Part B, we want to find the probability that someone, the question says, find the probability that someone scores between a 10 and a 15 on this Modified Dental Anxiety Scale. So I just wrote this in shorthand. We want to find the probability that x is between 10 and 15. By the way, it doesn't matter if it's inclusive or not inclusive. In other words, it doesn't matter if we write less than or if we write less than or equal to. For a continuous type distribution, they mean the same thing, because the probability that x is exactly 10 is going to be 0. All right, anyway, so let's draw a picture. That's always how I like to start these questions off. If you have a TI-83 or 84 calculator, it can do this very quickly with the normal CDF function. StatCrunch can do this as well, but I'm fine doing this the old-fashioned way with statistical tables. All right, So I like to double label my axes so I don't have to draw the curve twice. I know I'm going to need z-scores in order to go to the table. First, let's start off with the question at hand. We were told that x is between, oh goodness, not 30. This is from the previous question. Sorry, the mean is 11 of the x's, not 30. Sorry about that. All right, so normal distribution centered around 11. Again, I double label the axes so I don't have to draw the curve twice. We're told that we want to find the probability that x is between 10 and 15. Well, 10 is somewhere to the left of 11, so somewhere over here. And 15 is somewhere on the right over here. And don't worry too much about scale, as long as you have a number less than the mean on the left and a number more than the mean on the right. We're going to need to figure out the z-score for each of these numbers. We already figured out the z-score for 10, and that was negative 0.25. But we do need to figure out the z-score of 15 before we go to the table. So let's do that real quick. Let's see here. We have z-score 15, so it's going to be our x value is 15 minus 11 over 4. So that's just 4 over 4, which is 1. So this has a z-score of 1. We're 1 standard deviation above the mean at that point. So now we want to find this probability, the area between, and our table only gives us areas between 0 and a z-value. So we're going to break this up into two different parts. Let's do the left part first. So we want to find this region first. So I'm going to go to the z-table and look up 0.25, and I'm looking up a z-score this time. So I'm given that z is 0.25. So 0.2 for the row, 5 for the column, and I get 0.0987. So this probability is 0.0987. Okay, next let's find this, whatever you want to call this, the slashes that I made here, that region, striped region. So between 0 and 1, I'll look up a z-score of 1.00, and that's 0.3413 is the probability of having a z-score between 0 and 1. So the idea is we want to find the probability that x is between 10 and 15. Well, that's going to be the probability that x is between 10 and 11, plus the probability that x is between 11 and 15. So let's add these two together. Let me take out a calculator. So we have 0.0987 plus 0.3413, and I get 0.44. So that's our probability. One thing just to keep things straight, it can get confusing when you have z-scores and probabilities. What I like to do is I always like to do my probabilities up here somewhere and my z-scores down here somewhere. So I put my z-scores below the axis and my probabilities above the axis. This way I don't get confused. You never want to add z-scores together or subtract z-scores. They're just plotting points essentially, just points on the number line. Probabilities, though, you can add and you can subtract, and that's meaningful. So just be very careful about that. Okay, next question. Next part of this question is we want to find the probability that x is more than 20. Okay, so I'm drawing my curve again, still centered around 11. My z-score is 0. I want to find the probability that x is greater than 20. Well, that's going to be on the right and pretty far to the right as well. And we want the probability x is greater than 20, so I want to shade to the right. So this is ultimately what I want to know. So I'm going to start this off. If we're given an x value, we want to get a z value, and then we want to go to the table to get a probability. So that's the order, that's our procedure. All right, so let's get the z-score of 20. So let's see, it's going to be 20 minus 11 over 4, our standard deviation. So that's 9 divided by 4, which is what? Well, it's 2 1/4, so that's 2.25. It's a pretty large z-score. All right, again, warning about our tables, it only gives us probabilities between 0 and a z. So we'll look up this striped region on the table, and then we can try to figure out what the area of the tail is from there. So the striped region, I'm looking up 2.25 on the table. And I get 0.4878. So 48.78% of the curve is between 11 and 20. So if we want to find the probability that x is greater than 20, well, we know this whole region to the right of 11 is 0.5, but we want to subtract off these vertical striped area that I made. So we can do 0.5 minus the area we don't want to include, and that should give us that little tail that we do want to include. So 0.5, just using a calculator, minus 0.4878 gives me 0.0122. Okay, and that should be the answer. Okay, for 4.5, number 86, we're given a story again about tomatoes. I don't know how to pronounce any of these terms. Miraculin, it's a protein naturally produced in a rare tropical fruit, can convert a sour taste into a sweet taste. Thus, it has the potential to be an alternative low-calorie sweetener. Well, that's interesting. In Plant Science, in the May 2010 issue, a group of Japanese environmental scientists investigated the ability of a hybrid tomato plant to produce miraculin. For a particular generation of the tomato plant, the amount X of miraculin produced, measured in micrograms of fresh weight, whatever that means, had a mean weight of 105.3 and a standard deviation of 8, assume that X is normally distributed. So again, I wrote out this whole problem just in my shorthand up on here. So we're saying X is distributed normally with a mean of 105.3 and a standard deviation of 8. So three-part question. First part says find the probability that X is greater than 120. Okay, so let's see here. We're going to draw the normal distribution centered around the mean. The mean was told to us to be 105.3. We want to find the probability that X is greater than 120. Well, 120 is to the right of 105.3, so I'll draw it somewhere to the right. And again, don't worry too much about scale there. Double labeling my axes so I don't get confused. I do want to find the probability X is greater than 120, so let me shade to the right of 120. So we know we're going to need to go to the z-table for doing this via the statistical tables. So, and the table only gives me between 0 and z, so it's going to give me this region. I need to first find the z-score. So let's see here. The z-score of 120, so I can look it up on the table, is 120 minus the average, which is 105.3, divided by the standard deviation, which we were told was 8. So let me use a calculator here. 120 minus 105.3, that gives me 14.7. Then divide that by 8, and be very careful when doing these z-scores. Make sure you simplify the whole top before you divide. And I get 1.8375. I want to round that to 2 decimal places because that's how the table works. So if you're using the table, make sure you round the z-score to 2 decimal places. So we get 1.8375, so 84 is how it would round, since the 7 will round the 3 up. All right, so 1.84, and it is positive here, to the right of 0. Okay, next we can go to the table. Remember, our game plan is if we're given an x value, we can use the x value to get a z, and we can use the z to get a probability. Or alternatively, we could always go backwards. If we're given a probability, we can get an x value backwards by going through the same procedure. So if we're given an x, we use the z-score formula to get a z. Then from the z, we use the tables to get a probability. So that's the order in which we're going. All right, let's see. Look up 1.84 on the table. So the row is 1.8. The column is 0.04, so I get 0.4671. By the way, this is much, much easier if you print out the table. I didn't print it out, so that's why I'm struggling a little bit to read this. So this area here is 0.4671. We want to know we don't want to know that striped area, we want to know this shaded area here. Well, we know the whole area to the right of 0 is 50%. So if we subtract off the 0.4671, we should get the area we actually want. And that should give me 0.0329 if I did my subtraction correctly. Yeah. All right. For part B, we want to find the probability that x is between 100 and 110. So again, I'll draw my curve. Now, that's not the best curve I ever drew. It's still centered around 105.3. We want to find the probability that x is between 100, which is to the left of 105.3, and 110, which is to the right. So we want to find this shaded region. Now, because of symmetry, if the mean was 105 instead of 105.3, we'd be exactly halfway between, and we'd only have to do this once and then double the area. However, it is slightly off. In other words, the region on the left is slightly larger than the region on the right, so we do have to do this twice, even though it's not quite the way I drew it. So let's first find the z-score of 100. Okay, so it gives me negative 5.3 on top. Oops, it would help if I took out the calculator. 5.3 on top, divided by 8, and I get approximately, well, exactly negative 0.6625. I'm doing around this to to 2 decimal places, so I get negative 0.66. Okay, so that's that z-score. Let's find the other one. Let me do it over here. 110 minus 105.3 divided by 8. So that gives me 4.7 divided by 8. Okay, make sure you simplify the top first before you divide. And that gives me 0.5875, which would round to 0.59. Now let's just find each of these areas separately. Let me do the one on the left first. It doesn't really matter. So looking up a z-score of 0.66, so our row is going to be 0.6, and our column is going to be 0.06, and I get 0.2454. Okay, similarly, my other z-score is 0.59, so 0.5 row, the last number in it is 0.2224. And by the way, just a sanity check, I said that the area on the right should be slightly smaller than the area on the left, and that is what I got. But we want the area together, and if you want to do things together, you add them. So let's add those two areas. So 0.2454 plus 0.2224 gives me 0.4678. So in other words, the probability of the tomato having between 100 and 110, whatever the weight, microlugnin, whatever, is 46.78%. All right, part C. We want to find some value, some x naught value, or in this question they're calling it a. We want to find some a value such that the probability x is less than a is only 25%. So drawing this out, I'm just drawing my curve. Okay, we want the area to the left of our a value, whatever our a value happens to be only 25%. So that's going to have to be somewhere on the left-hand side. And maybe this area looks to me about to be 25%. And we want to find this value here, which they're calling a. So going back to our procedure here, we can go from an x value and get a z using a formula. We can go from a z to a probability using the table. But we could also do this backwards. If we're given a probability, we can use the table, but use the table backwards to get a z-score. And then we can use that inverse z formula that, that I mentioned in the last question to get an x value. So we can use this backwards as well. All right, so let's do that. Well, first, tables only give us areas between 0 and z. So we'd have to actually look up this area on the table. We know the area to the left of 0 is 0.5, but we don't want to include this tail, which is 25%. That means there's 25% left over in those horizontal striped area. So this area here is 0.25. And notice 0.25 plus 0.25 is the 0.5, which should be to the left of 0. All right, so I'm going to look up 0.25 on the table, but I'm looking it up in the probability section in the meat of the table. And you may not find the number exactly. So 0.25, the closest number I see, well, I see a 0.2486 and a 0.2517. 0.2486 is slightly closer, so I guess I'll use that one instead. And that's associated with a z-score of 0.67. So this z-score will be 0.67. But wait, since it's to the left of 0, it is going to be negative. And we do need to think about that for a moment, because remember, our table only gives us positive z values, but they'll still work for the negative ones. So we do have to think for a moment whether it should be positive or negative, and it should be negative because it's to the left. So now we can use that inverse z formula to figure out what our x value is, or in this case they're calling it a. And remember, our formula is x equals mu plus z sigma. So using this formula, we can figure out what a is. Well, they're calling this x value a, so we can say a is equal to the mean, which we were told was 105.3, plus z sigma. Well, plus a negative is going to be a minus. It's actually all been minuses so far, but that's just coincidental. So minus 0.67 times sigma, which is 8. And then I'll need to take out a calculator. 105.3 minus 0.67 times 8, and I get 99.94. And this is going to be slightly off because I had to make that rounding when I found the z-score. So a is going to be approximately 100, we could say. But my stat lab will accept this as an answer. For 4.5, number 96, we have the following question. Almost all companies utilize some type of year-end performance review for their employees. Human Resources, or HR, at the University of Texas Health Science Center provides guidelines for supervisors when rating their subordinates. For example, raters are advised to examine their ratings for a tendency to either be too lenient or too harsh. According to HR, if you have this tendency, consider using a normal distribution, where 10% of employees will be rated exemplary, 20% distinguished, 40% competent, 20% marginal, and 10% unacceptable. Suppose you are rating an employee's performance on a scale of 1 being the lowest and 100 being the highest. Also assume the ratings follow a normal distribution, with a mean of 50 and a standard deviation of 15. Well, based on these, let's answer several questions. You should have 20% be distinguished, 40% be competent. I'm sorry for my shorthand here. 20% be marginal, and 10% be unacceptable. We're also told that suppose you're using a rating system where on a scale of 1 to 100, where 1 is low and 100 is high, assume that ratings follow a normal distribution. So X is distributed normally with a mean of 50, that's the mean, and a standard deviation of 15. And again, this is just my shorthand, so I don't have to write out a whole bunch of words. So what is the lowest rating you should give an exemplary employee if you follow these guidelines? Okay, we can do this. So we want to know the lowest rating for exemplary. Okay, so let's draw a normal curve. And we know it's centered around 50 because we were told that. told about exemplary? We're told that 10% of employees should be exemplary. So whatever score someone needs to be exemplary, like maybe it's 90, maybe it's 80, maybe it's 60, I don't know. But whatever score someone needs to be exemplary, only 10% of employees should be making that cut. So only 10% should be above it. So we want the area to the right of our exemplary mark, wherever it is, to only be 10% of our curve. So we know this area has to be 0.1. Now, using our procedure that we've been developing, if we're using the statistical tables to do this, we know that if we're given an x value, we use the z-score formula to find a z value, and then we use the statistical tables to find a probability. But we were actually given this the other way. We were given a probability, so that means we have to use the tables, but use the tables backwards to find a z-score. And then you take that z-score and use that inverse formula, the x equals mu plus z sigma, to find an x value. So let's use this procedure. So first we're going to be using the probability to find a z-score. But that's not the right probability. Our z-table only gives us between 0 and z for probabilities. So we need this region here. We're told that this area is 10%, which means that this vertical stripe area has to be 40%, so 0.4, because remember, half the curve is to the right of 50. All right, so we're going to look up 0.4, but we're looking up the 0.4 in the probability part of the table. So the closest number you can find. And the closest number I can find is 0.3997. That's really close. That's really close to 0.4. And that happens at a z-score. So looking at the row, it's 1.2, and the column's 0.08. So that's associated with a z-score of 1.28. Now, using our formula that x equals mu plus z sigma, we can plug in our values to find what the minimum cutoff score is for exemplary. So our mean is 50, our z-score is 1.28, and our standard deviation was given to be 15. So x equals, let me take out a calculator, 50 plus 1.28 times 15 gives 69.2. So that's the answer. The minimum score to get exemplary is 69.2. Part B is a little trickier, though it's a very similar question. It says we want to find the lowest score for competent. Now, we know that 10% are exemplary, 20% are distinguished, and 40% are competent. So that means a total of 70% of employees are competent or better. So how do we draw that? Well, we're going to start off by drawing a curve, just like before. But we want 70% to be above our mark. Well, we know half the curve is to the right of 50, so we need to go beyond that. So that's going to be somewhere down here. So we want to find where this line is. We know that 50% is here, which means 20% would have to be here in order for this total area to be 70%. The idea is if we just do 0.7 minus 0.5, we get that 0.2. So we know the whole area to the right of our whatever our score is going to be 70%. Subtract off the 50% that we're not looking up on the table, and we're left with the 20% as this region here. Okay, so now let's go to the table and look for a probability close to 0.2. Not finding one super close. And again, they do go in order. So I have one that's 0.1985 and another one that's 0.2019. They're both kind of far away, but the closer one is 0.1985, so let me use that instead. And that has a z-score of 0.5, and then the column is 0.02, so 0.52. All right, yeah. So 0.52 is our z-score. And again, our table only gives us positive z-values, so you have to pause for a moment to think, should this z-score be positive or negative? And it should be negative because it's to the left of 0. Remember that getting competent isn't necessarily a great score, and especially the lower end of competent. All right, so now we can use our formula, x equals mu plus z sigma. Our mean is 50, our z is negative 0.25, sorry, negative 0.52. So plus and negative means subtraction. So minus 0.52 times our standard deviation. Okay, and taking out a calculator, 50 minus 0.52 times 15 is is 42.2. So that's our X value for the minimum score you need in order to be rated competent.